Well, good evening, everybody. My name is Mike Wilson. I am the Executive Director of AIA East Bay. And tonight we have Weldon giving us a presentation here. Jeannie Huntsman, thank you for agreeing to speak to us this evening. I'm going to hand it off at this point. Two notes. One is Jeannie's pretty open with questions throughout her presentation. So she's inviting you to ask questions. You can do this three ways. One is raise your hand by using the icons in your toolbar. Two, type your question into the chat bar, and then we'll call on you when the time comes, and you have the choice to either have Jeannie read your question back to the audience, or we'll unmute you and let you read it. So please don't hesitate if a question comes to mind to please enter it into the chat. At this point, I'll leave you to Jeannie. Thank you.
Thanks, Mike. So as Mike mentioned, I'm Jeannie Huntsman. I'm with Willdan. I'm a licensed architect and energy consultant, and I work on the California Energy Design Assistance Program, or CEDA, which is offered across the state of California on behalf of our investor-owned utilities, PG&E, Southern California Edison, SoCal Gas, and San Diego Gas and Electric. So for those of you who have participated in the past in the Savings by Design program and haven't heard of CEDA, the CEDA program has replaced the Savings by Design program. It's a free program that provides decarbonization consulting and incentives to help you maximize your new construction and major renovation projects decarbonization potential. So if you're interested in more about the program, happy to talk after our presentation is done about that. And you can also enroll in CEDA by visiting our website at californiaeda.com. And I'll have some more contact information at the end, last slide that we have. So it looks like we got a little bit of background noise, so just want to make sure folks are muted. So we've got our abstract and learning objectives. I'm not going to go through all of these for you right now because you guys probably all saw them in the marketing objectives or marketing send that went out. So I'm going to just jump right into it and talk about why are we talking about carbon. So on the left, you can see that the buildings account for about 40% of all carbon emitted globally. And then on the right, we're looking at how that breaks out between embodied carbon and building operations. 28% is used in the activities supporting the construction of buildings that embody carbon, and 72% is used in the operation of buildings. And in this session, we're going to really focus on operations, as you might expect, since our program that we run is sponsored by the utility companies. So it's tough out there, right? As architects, we value sustainable design and understand the impacts buildings have on the environment, but clients aren't interested or asking for it. Budgets are tight. Developers don't care about ongoing maintenance and energy costs. Paybacks are too long. Timeline is too short. Contractors aren't comfortable with it, nor facilities managers. Measures just get removed of value engineering. It's not really in our scope of work. Maybe it's just the engineer's problem to solve and it's not required by code. In practice, I've used all of these reasons as ways to push past sustainable design and frustrations when those things that I wanted in the project didn't end up in the project. So I've used many of these reasonings myself in projects or run into them. But I question, though, if we really solved a client's design challenges, if we turn them over a building that's going to depreciate at a faster rate than others in the market and has a lower net operating income or profitability, is more vulnerable to weather events and at risk of becoming a stranded asset as the cost of maintaining gas infrastructure is becoming fairly high, or has some occupant comfort issues. So that's why we're going to talk about carbon today. And so during our call today, you're going to hear me talk about a few rules of thumb when considering energy and carbon use in buildings. There's some good ones out there, but there's a word of caution that I like to bring up about rules of thumb in that they aren't static. Every building is different. Every owner, every user, and even the facility staff is different. which means that each building operates and is used differently. And so I think many of you, if you've been in the industry for a few years, you know that everything's changing and the pace of change is speeding up. So what we do today, how we design and the equipment we install might be very different now than it was even a year or two ago. So I'm going to try to give you some rules of thumb about thinking about carbon in today's environment with current information. So I hope you'll indulge me a little bit of a history lesson, because I wanted to explain that electricity is a power source is really relatively young. We've known about electricity since ancient times, but we've only really harnessed its power for about 250 years. And really things started to take off when Edison brought electric lights to those who could afford it in the 1880s. At that time, it was really a luxury for a privileged few. And by 1925, only half of US households had electricity. My own personal grandmother was born in the early 1900s, and her fondest childhood memories was the exciting day her family got electricity at their home. She said it was magical. She was really also thrilled when she moved into her first home and her husband Bill finally bought her that electric washing machine for the new house. It was a real time saver. She was super excited about it. She used to talk about it a lot. And, you know, Bill was also excited when he got cable TV just in time for retirement. And Grandma thought that was a real time saver as well, because she was adjusting to Bill being home all day, and having TV allowed him not to bug her as much. So by the time she passed away at 100, she was reading books on her iPad and using FaceTime to video chat with her great-grandchildren. So in one person's lifetime, technology changed so much from electricity being a novel thing, something magical, to something part of everyday life. So I just kind of want to pause and let that sink in. I know a lot of times we talk about rules of thumb for electricity, but it's really a young technology. Electricity provides safe light around the clock. It cools our buildings on hot summer days and heats many of them in the winter. And it quietly breathes life into the digital world we tap into with our smartphones and computers. Our perception of electricity has changed over time. In the beginning, we used it conservatively as it was new and had a high cost and shouldn't be wasted. It had an intermittent disruption, and we tolerate that. Over the years, electricity became a lot more affordable and reliable and accessible. And today we have the expectation that power will always be on and will always deliver the amount that we need when we need it. And we're frustrated and angry when it's not available and we don't have a plan in place to live without it. That's a huge swing in perception that occurred in approximately 100 years. So when you're thinking about rules of thumb and rules of thumb in the past, remember that it's hard to rely on rules of thumb when technology and the energy grid is changing so quickly. So electricity needs to be consumed the moment it's produced, because grid scale storage is still costly and limited, making a lot of advancements there, exciting things to come. But as consumers, we do not use or receive electricity in a constant stream. We demand it at different times by plugging something in or turning it on. This constant fluctuation makes it really hard to predict how much energy to produce. So to meet demands, utilities separate generation into two general segments. There's base load and peak load. Base load on the grid is the minimum level of demand on the electric grid over a span of time. So for example, 1 week, because some more cost-effective power plants are harder to ramp up at a fast rate. The remaining demand is varying throughout the day, and it's met by systems that turn up and down quickly. So system operators prefer that flat energy profile with a few small hills and valleys, because it allows them to operate a system smoothly with the least cost. That's not the load profile we have in California. With the widespread solar impacts, the load-shaped California grid operators are seeing has very deep gorges and steep mountains. This shape is also called the duck curve because of the way it looks on the chart, looks like a duck. So this is between 4 p.m. and 7 p.m. There's an increasingly steep ramp up of demand, currently met mostly with natural gas power plants. And then the solar output begins to drop right before that peak load during the day around 6 p.m. So solar is not helping us out in the dirtiest points of the grid. So that variable solar needs to be balanced with either dispatchable power generation or flexible demand. This scenario does not create profitable business models for the electric companies, forcing them to raise rates. And a few ways to solve this is to build load midday to raise that belly of the duck down here at the bottom here, which keeps getting deeper and deeper as we add more solar. And we can do that with electric vehicles and electrification, or we can shift the load by incorporating grid scale battery storage, still working on that, but it's a technology that's in the near future. Or rewarding customers who shed and shift load off of peak demand. So today's energy mix in California is cleaner than the national average. It includes less coal, more renewables, and more natural gas. It will continue to decarbonize with non-dispatchable solar and wind. However, the duck curve is going to continue to grow as solar gets cheaper and is being mandated in certain building types by the Energy Code. Now, I'm not trying to say solar is bad. I think it's a great part of the grid and it's helping us decarbonize. It's just we got to think about where it fits in this balance. And it's not the solution that's going to solve everything. So as tomorrow's grid continues to evolve and gets a lot cleaner, and there's an awful lot of improvement plans out there for the electric grid, the use of coal in electric generation is being replaced with renewables and natural gas plants. There are restrictions happening, as many of you probably know, on new natural gas hookups just popping up. Lots of questions about the validity of some of them from a legal standpoint, but they're still becoming more prevalent. And then interestingly, the California Public Utility Commission recently retired subsidies on all new natural gas connections starting July 1st of this year. So the cost of gas infrastructure is about to become a little bit more visible. We're starting to see new incentives to encourage electrification, including the CETA program and also some state and local government incentives. Renewables are becoming more cost effective and technology continues to advance, making adoption easier and faster. We're also getting closer to utility grade battery storage and distributed battery storage. And all of that combined makes the grid of the future cleaner and more resilient than the grid of today. So as the grid changes, so too will rate structures. Demand response programs provide financial incentives to customers to reduce consumption during peak incidents. And time of use rates are starting to pop up where you pay per kilowatt hour charges throughout the day, with the highest charges happening during the peak hours, encouraging customers to reduce loads when the grid needs a little bit of relief. So I'm going to jump back to rules of thumb for a moment, especially that word of caution of making sure our rules of thumb are valid. So when we're looking at rules of thumb or relying on manufacturer literature or comparing an energy profile of your building to other buildings, it's important that we compare apples to apples. So climate, building type, function, form, and size, even subtle differences like window to wall area ratio, hours of operation and usage all have a profound impact on how individual energy and carbon reduction measures perform in a building. So on the right-hand side of the slide, we've listed some of the many building components that play into energy and carbon. And a key point here is they all interact with each other, and each component or system can affect how we think about building and design and the other parts of how we think about the other parts of a building. So I think I've got a question here. What % of the natural energy that California uses is brought in from other states? I don't have that percentage off the top of my ahead here, but I do know that we bring in California some energy from other states. But I will kind of take down that note, and I've taken down your name, Linda, and I will see if I can get you that percentage. Just going to check here while I'm at it, make sure there's no other questions. All right. So as I mentioned earlier, the pace of change in our industry is rapidly continuing, and a big part of that is the change in technologies we have available. Some potential decarbonization measures include both ground source heat pumps and air source heat pumps, variable refrigerant flow systems, or VRF, heat pump water heating, and electric kitchen equipment are all helping us decarbonize. When I personally started in architectural practice, a lot of these were new or weren't really widely adopted. We're seeing a lot more uptick on these, particularly central heat pump water heaters in multifamily buildings. So we've had to build up our familiarity with these systems and find ways to decide whether they made sense for our particular project. So how do we know which measure will have the most impact, especially as we focus on carbon? Rules of thumb can get us a conversation started, but to really dig in for the specifics of each project, I strongly recommend energy modeling. So to kind of recap what we've talked about so far is that rules of thumb alone aren't going to solve this challenge. Electricity is a young technology. The electric grid is continuously evolving. Our current structure is not a sustainable business model, and rates are going to keep changing. There are too many variables that impact energy use in a building for a one-size-fits-all solution. And building systems technology keeps evolving and improving. So what's our pathway or blueprint that we can use to work towards decarbonization on your projects? Well, I think I already spilled the beans here and said I think energy modeling is the way to go. The tools we use to analyze how our projects interact with the grid are advancing as well. They've really become a lot more they become faster, more accurate, more versatile, easier to use, and affordable than they have in the past. When I first started practicing, I did a lot of low-income multifamily housing. I would have never been able to afford to do an energy model on that type of a project 20 years ago. Now it's affordable and more commonplace to do an energy model, not just for code compliance, but for analyzing which strategies make the most sense. And what's important about using an energy model is it can really respond to the changing energy industry at a local level. So when we're doing an energy model, I recommend that we do a comparative analysis. And what goes into a comparative analysis is you take your building geometry, your hours of operation, some assumptions on how the building will be operated and occupied, an average weather file, and then minimum requirements to set what the baseline or starting point is that we're going to compare against. All of these factors together equal the results. Thinking about energy models as comparative is important. We're not trying to dial in exactly how much energy a building will use or how much carbon impact it has, but rather we're looking at to see which measures, which systems, which components will have more of an impact than others, so that we can make an informed decision on what to include and what might not be as important. So models are perfect, right? Well, it depends. They are 100% accurate, provided you can accurately predict the three main variables, which are human behavior, climate and weather, and energy prices. And if you can do that, then you might want to get in the stock market. So here I wanted to illustrate that, a model in early schematic design phase can be very useful, but we have a little bit less, slightly less confidence in it than one that's built during occupancy. But early design models aren't intended to predict exact energy use. They're intended to help us make informed decisions. And I had a question here. Who, if any, offer no-cost, low-cost, subsidized, or free energy modeling tools, open source modeling capabilities? I think the CEC offers a list of tools. Willdan has our own tools, the Net Energy Optimizer. We will do a free carbon analysis if you participate and are eligible to participate in the California Energy Design Assistance Program. So that's one way to get a free energy analysis. The Department of Energy has a listing of free energy tools that are available. I think I recently heard of Slipstream maybe was testing out some energy models or tools that are offered online as well. So there's a lot of different options available out there. There's paid versions, of course, as well. It just depends on what your needs are and what you're trying to achieve with your model. So when I'm trying to think about how I'm going to decarbonize a building, I'm really looking at starting as early as possible and analyzing things in schematic design, such as massing, glazing, insulation, and the overall general HVAC concept, because those can have a significant impact on the long-term carbon use of a building over its lifespan. So once you've minimized your base load, those really high-level conceptual designs, particularly the HVAC concept and the envelope design, then you want to start to minimize your loads further by implementing simple, cost-effective systems to reduce energy use during that design development stage. So if you're looking to do some comparative analysis, best to do it in schematic and early design. And these types of models are rough cut and don't need to be as costly as the fine-tuned code compliance models that you might see submitting at the end of construction that are a little bit more complex to build. And so once you really minimize the total load as much as you can with energy efficiency, I would say then is a time to start considering how you might want to further reduce that load with on-site renewables, solar, wind, and cogen. And then at the end of the day, we all have to remember that people are going to operate these buildings in ways that we could never imagine. So I'm sure you've all seen some examples of that. And operational strategies can cause rapid reduction of energy consumption, but they do need to be managed on an ongoing basis. And so really, we're going to focus on these first three buckets today, which is minimizing that load as the first priority, using simple, cost-effective systems, and then having your appropriate energy source to further minimize that load going on. So I want to look at a few case studies here as we're trying to decarbonize and work out what works. We've built a few case studies that we've looked at in the California market. And before I do that, I'm going to pause and read through the chat here. Are low-income owners of existing stock? Certainly, I think there's programs that are available and tools available for affordable housing and low-income projects. So I think that a lot of the new programs that have come out from the utilities are specifically tuned to disadvantaged communities. And I have a personal passion for affordable housing. I spent first half of my career designing and developing affordable housing developments with HUD and low-income housing tax credits. So if you do have questions on that, I'd be happy to, my contact information will be at the end of the presentation. I'd be happy to chat with anybody about how we can make affordable housing more energy efficient and reduce carbon. All right, so moving on to case studies, we've got 4 different building types that we've put together here. We took a typical apartment building, a typical school, a typical office, and a typical clinic project. We use kind of typical space assets that go into the building, a pretty generic 100,000 square foot program for each, and some standard hours of operation that we find in these types of facilities when we're modeling them. And I should note that Willdan runs new construction energy efficiency programs across the nation, and we probably see about 2,000 projects a year. So we see a lot of energy models. So we've got a big database to draw from. So when we're looking at these case studies, we thought we'd pull one building in San Jose and model another one in Los Angeles, just to see if there was any variability between the two cities. We modeled 3 different HVAC systems. The first one was a natural gas system, which was a VAV system with air-cooled chiller and gas boiler in all the building types except the apartments. In the apartments, we used some gas-fired magic packs with packaged rooftop units in the common areas. And then for the water heating, we used gas-fired water heaters. Then for the electric systems, we used air source heat pumps with electric backup and electric resistance water heaters. Then we thought we'd throw out a really high-end renewable option there with ground-coupled water loop heat pumps, which may not always be the best solution in some areas in California, but we just thought we'd throw it out there. And then we put on some heat pump water heaters on that one as well, just to really maximize things. We use some typical system assumptions. I'm not going to read all of these off to you, but if you're curious, this is what we put in for our mechanical assumptions, kind of common things we're seeing built in the market, these levels of efficiency, demand control ventilation where it was applicable. For architectural, we did slightly above code minimum because we find that the code has kind of hit a sweet spot on R values for roof and wall. And then aluminum windows, where we put slightly above code minimums for U factors and solar heat gain coefficients. And of course, in the apartments, we use vinyl windows as is pretty common. And then for our lighting assumptions, we used LED lights throughout because that's pretty saturated in the market. And we use lighting controls as required by code. So my first set of charts here, and I'm going to have a lot of charts that are going past. So I'm going to try to slow down a bit and walk through those a little bit more for you guys here, but don't be afraid by all these charts. There's some simple analysis that's coming out of this. So the first one here is our annual carbon emissions by energy source. And this one's the multifamily project in Northern California or San Jose. And so here we've got this first 4 buckets of charts here are the current annual emissions if you looked at the grid on how it's operating today. The gray bar is the worst performing building you could build to code today, provided you're not one in the stretch or reach code areas in California. So this is sort of the worst statewide performing building that you could build. And then our next orange and yellow bars here are the natural gas systems, that conventional natural gas system, which would, for the multifamily, was the magic pack systems. And here we've got this darker orange, which indicates the input of the natural gas to the carbon emissions, and this lighter sort of yellow color is electricity. And then moving on to the blue bar here, this is the air source heat pumps. And there we were illustrating just all electricity because there's no natural gas in that option. And then finally, the third option was that ground coupled heat pump with that heat pump water heater, that highest renewable option. And that one again also has no electricity. So those bars are how things play out from a carbon emission standpoint for the current annual emissions with the grid we have today. And as you can see, that the lowest carbon output is, of course, that ground coupled heat pump system, followed closely by the air source heat pump, and you're using more carbon with the natural gas systems. Now, if you look at what the average emissions are expected to be over 30 years with the projects that are already in place to clean the grid up over that 30-year time span, what we see is that there's further reductions in the carbon emissions in the all-electric systems, but less reduction in those gas systems. That's because the electric grid is getting cleaner and natural gas is not. So then if we look at what is the estimated annual 2050 emissions, and this scenario looks at if the grid impacts that we're planning all get put in place and we just kind of did like a medium level expectation, because there's a lot of different models out there what the grid at 2050 is going to look like, but we just kind of took an average one. So we didn't want to have the highest performing one, which could get us to net zero carbon on a lot of these all electric systems. We took a good average model of what's expected to be on the grid in 2050, as we think that one will be fairly achievable. And here we can see that the natural gas systems are really kind of stuck when their carbon outputs, where the air source heat pump and ground coupled heat pump are really very close to hitting that net zero threshold for carbon emissions. Throw a little bit more solar on those buildings, and I think we get there. So that's our multifamily in Northern Cal. We're going to see it look very similar in Southern Cal. I was a little disappointed because there wasn't huge differences between Northern Cal and Southern Cal in these charts. You just see that you have a little bit less emissions down there in Southern California because you have a more temperate climate. All right, so then we're going to look at the K through 12 or school that we put together, and here you can see that if you just followed code, you could build a pretty poor performing building from a carbon standpoint, but you can build a decent building using natural gas. However, if you really wanted to get to that near net zero emissions, you've got to go with that all electric system. Similar outputs here for Southern Cal. No big surprises. And then as we look at the emissions for office buildings are quite a bit lower than they are for multifamily or for the K through 12 schools. But still here is a similar trend, a little bit closer in current annual emissions on the natural gas than some of the other building types, but really the impacts on those come out in 2050. And then finally, we've got the office in SoCal, similar trends, although a little bit closer. You pop up a little bit on the air source heat pump system. I think there's some more fan energy there, which makes that look roughly about the same as the gas system. And then the interesting one to me was the healthcare clinic in Northern Cal, where you start to see that if you're looking at it today and only at today's emissions, that a gas system is about the same carbon emissions as a ground coupled heat pump, which tells me ground coupled heat pump is not the right HVAC system for healthcare. And if any of you are healthcare designers, you probably already know that. And then, maybe air source heat pumps are not quite the right system. There's some other options there that we could look at to really help us drive down the energy use there. We're going to dive into that one a little bit more. However, as you get to 2050, it's still the best option to get as closest to our zero carbon emissions is going to be those electric systems. Similar situation here in Southern Cal. We got a question on PV arrays here, so I'm just going to pause a bit and another question here. So the grid projections do take into account growth overall. So the question was, since the population in California has doubled since 1980, do those projections take into growth? The models that we use were a Cambria model for carbon emissions, and they do take into account various growth models. So it's a very complex model. And then PV arrays becoming more prevalent as carbon reduction strategy. How does that approach compare to the technology system in your charts? And also, could you comment on the carbon reduction strategy when viewed to include per dollar spent on carbon on CO2 emission reduction value factor? I haven't done the analysis on per dollar spent. That's an interesting way to look at that. I'm going to take that one back with me and probably do some analysis, but certainly if you participate in the CETA program and talk through with your team on that, they'd be happy to do some analysis there. We love running numbers, so I'm just going to write that one down. I'm going to get into carbon or I'm going to get into PV in just a minute. So key takeaways here that are installing natural gas equipment in new buildings locks in the carbon emissions for the life of the equipment. And the electric grid is getting cleaner each year, which has a profound impact on the carbon emissions of the built environment. Installing efficient electric equipment is going to allow the building to decarbonize along with the electric grid. And electrifying buildings is a key to decarbonizing the built environment. So now I'm going to look at the impact of solar energy. And I didn't do this on every single chart because I didn't want to bore you guys with what this looks like on every single building type. But I think you can see that the trend will be that renewable energy the offset is what helps us get to that further reduction in carbon emissions. So if we look at here, the chart, the sort of white piece at the top that's got a blue line around it, that was what the total electric load was prior to adding on renewables. So that white box is really that difference in renewable. You do see a diminishing return on carbon savings over time for PV, but it's still really important in reducing energy costs over time for customers. So it's really about the long-term energy costs as well as getting to that net zero carbon. It's a piece of the puzzle. And I just encourage you to spend the money that you can first on making your building as energy efficient as is feasible, and then add in solar on top of that. And I think you'll have the best building from a carbon emissions standpoint. That diminishing return on carbon, it's going to get a little bit less as the grid gets cleaner. It's still a key strategy for reducing annual energy costs and is required by code for certain building types. So really electrify as many of those end uses as possible first to receive the maximum benefit of solar. And then what's really going to be interesting is when we're able to pair battery storage with solar, because that's going to really help us cut operating costs as these time of use rates coming out are going to encourage people to reduce their use at peak demand times, and batteries are going to be a good pairing for that. So if you can pair your solar with battery storage, you're really going to be ahead of the game where it makes sense. Now that's a newer technology. We're still testing it out, but it's something that I see coming through in the future. One of the important things to remember is that solar is providing energy at a time when the grid is already pretty clean, but it's not providing you with the energy when the grid is pretty dirty. So if you can have that battery shift that load that you collected from the solar off to later at night when the grid is a bit cleaner again, then you're going to have the maximum benefit from a carbon output standpoint. All right. So The next piece we dug into was really trying to understand how carbon is broken down by end use. So going back to that multifamily project here, what we've done is we've taken this conventional gas system, the air source heat pump system, and the ground source heat pump system, and we've broken out what was the carbon impact for each end use in the building. And those end uses are heating in the red at the very bottom. Blue was cooling. That light gray box is fans. There's some thin bars over in the ground source heat pump that is pumps. Pumping energy is usually required in that sort of system. And then this large green bar in this particular example is the water heating or district water heating for the project. And then the small yellow bar is lighting, and the light yellow is plug loads. So as we can see in multifamily, if you want to decarbonize a multifamily building, you should focus first on water heating, because that's going to be your biggest load. And there, I really recommend utilizing a central heat pump water heater. And the savings from that central heat pump water heater are really showing up in that last option, that ground source heat pump option, because we threw a central heat pump water heater into that option for the water heating to maximize that renewables. I think if I did this chart again, I probably would add in another scenario here to show what the air source heat pump system would look like if we put that central heat pump water heater there. And there you'd see that green bar reduce about as much as it did in the final option for the ground source, but still quite a significant reduction in carbon emissions from the natural gas system. So you probably hear the New Buildings Institute and a lot of other Building Decarbonization Coalition speaking a lot about central heat pump water heaters and heat pump water heaters in general. I personally have one in my house and I love it. I've been saving a lot of energy and I just love everything about that water heater. But that's why the push is there, is because this is the biggest area where we can improve carbon reductions in a multifamily building. Similar scenario in SoCal, except there's a lot less heating load, as one would expect. Slightly more cooling. And then we're going to jump over to the office building. Here in the office building, it starts to kind of let me know that the systems that we picked weren't maybe the best systems for the office. And how I see that is, if we look at the conventional gas, we've got a really high heating load that we've reduced by using the electric system. We've reduced the emissions from that using the electric. However, the type of system we used was a distributed air source heat pump system, which increased the fan energy of the building. And so if we really wanted to get back to that lower fan energy that we're seeing in the first option, we could try utilizing a heat recovery chiller instead. And I think there that we'd see a big reduction in the fan energy and a further reduction in the emissions of the all electric option. So that would be something to consider. Here also, some attention could probably be had to plug loads and the ways that we could reduce the plug loads in that building to really reduce carbon. And there's still some work to be done on lights. I probably would spend the money on a heat recovery chiller over a geothermal system for the office to get rid of some of that fan energy. Similar situation in Southern California. And then if we jump over to the schools, pretty evenly balanced loads. So we might need to tackle all of it. Kind of taking a look at that water heating there as well. The air source heat pump being a distributed load might be something to look at the fan energy and what we can do to reduce that. We still got some decent lighting items to tackle. and also some plug loads. So, schools can be a little bit more work, but also very important to reduce the emissions from them because they're going to be around for a long time. Similar in SoCal for that school. And then in the carbon emissions for healthcare, here we can really see that plug load is pretty high. There's still some decent fan energy we've got to work on. So these are trickier buildings to work through because those plug loads are generally life-saving equipment, and so they're important and maybe where we want to spend our emissions instead of in the schools or multifamily. Similar here in SoCal. So water heating is the biggest carbon usage in apartments and school facilities. And plug loads and fan energy in offices and healthcare are opportunities for carbon reduction. There's minimal savings impact left from lights as LEDs have made electric lights very efficient, but still some opportunity. And then a fun fact for you, in the next 5 years, according to Construct Connect Insight, 460 million square feet of new construction apartments are expected to be built in the state of California. So we really got to work on those multifamily projects and making them as carbon reductions as small as possible, or making their carbon usage or emissions as small as possible. So a few other considerations, keeping in mind that the buildings we're building today are going to be around in 2050, hopefully. And so they're likely going to have maybe 2 replacements of the HVAC system, 3 replacements of the water heating system. So always best if we can put our best foot forward and put the best system in place now. They're likely going to get 4 replacements out of the electric lights. So just kind of illustrating to you, the building's going to be around a long time. So maybe spending a little bit of time with the envelope is important, not just from an occupant comfort standpoint, but from reducing your emissions at the beginning. So talking a little bit about that, we're looking at dialing in carbon reduction. I like to bucket building loads into 2 categories. First is external loads. That's the way buildings lose or gain heat from the outside, which is really influenced by the quality of the building envelope. And so focus on that piece can help us reduce the sizing of the HVAC equipment and the costs of the HVAC equipment. And then there's internal loads, which account for the internal heating of that comes from electric lights, as well as the occupants, which is really the nature of the building type drives that. And what I mean by that is that building types house different activities, and that influences the heating and cooling load. What occupants are doing have very different heat outputs. And as you can see, a person sleeping in a hotel room versus exercising in a hotel gym has a heat factor increase of about 5. So understanding how people and their activities influence internal loads can help us identify why a load in one area is different than another, and try to dial things in to maximize our carbon emissions reductions. So finally, the building envelope impacts heating and cooling loads and has a long lifespan. And additional carbon savings can be found by striking a balance between envelope strategies and project budget and goals. And additional carbon can be found when we analyze the impacts of internal loads. And decarbonization analysis can help identify areas where savings can be found. So for some conclusions here is just a reminder that we want to minimize that load first as early as we can in schematic design, and use simple, cost-effective systems that we develop in design development to really minimize that load as much as possible before we start putting the budget towards renewables such as solar. And then just remembering that people are going to operate these buildings in ways we can never imagine. And so operation strategies can cause that rapid reduction of energy consumption, but they need to be managed. And I noticed that some savvy business owners are having an interest in continued relationships with their design teams or utility partners to monitor that energy use, as it becoming quite costly, and rate structures are becoming a little bit more complex. So there's more of an interest there in monitoring that. So something to look forward to in the future is a potential way to increase your relationship with the building owner. So finally, the landscape of power generation is changing and contributes significantly to carbon reduction, and encourage you to utilize energy modeling to explore load balancing and carbon emissions, assess carbon reduction with today and future emission rates to design buildings for the future. Don't just look at today's emission rates, because that's not going to give you the full picture. And make a commitment to include low carbon design strategies in the development of every project. There's a lot of resources out there to help. There's the new state charges with the carbon reduction have really opened a lot of great programs up. So if you ever have any questions about that, we're always happy to help you out at Willdan. Again, you can find us on californiaeda.com, or just give us a call at our main line. Any of our teammates will be happy to help you guys out in trying to figure out this challenge, because we're all deeply vested and interested, and we love to run analysis. So thank you, everybody, for your time tonight on this listening to this presentation.
And thank you, Jeannie. We really do appreciate you taking the time to share this great information with us. And for those of you here, last chance to ask questions. Time's almost up. A lot of thank yous. I'll add mine to the pack as well. And you all have Jeannie's information, so if something comes up later, please let us know. One final note, this got you 1 credit for the zero net carbon design statewide licensure, so you'll get that 1 hour credit provided you attended at least 80% of today's event, and those will be submitted shortly after this event, within a few days. Anything else to add, Jeannie?
Nope. I just thank you guys all for your interest in decarbonization, something I love to talk about.
All right, everyone, have a great evening. Bye now.
Thank you.